our manufacturing process, we have a hole punch machine that's set up to punch a hole 1.84 centimeters in diameter. This hole is punched into a strip of sheet metal as part of the process. The strip of sheet metal is then creased and sent on down the assembly line to the next phase of production, where a metal rod is slipped through the hole. It is very important that the hole is the specified diameter, otherwise the metal rod may not fit if the hole is too small, or it may not fit securely if the hole is too large. So to test the accuracy of this machine, technicians randomly took 12 pieces of sheet metal off the assembly line and measured the holes punched in centimeters. The data is given below. The technicians would like to test the hypothesis that the average or the mean is equal to 1.84 centimeters. To start out our hypothesis test, we will clearly define our hypothesis statements. Our null hypothesis, which deals with equality, is that the average is equal to the specified diameter of 1.84 centimeters. The alternative hypothesis deals with the specific case. In this case, we are not told whether too large or too small specifically, but we are just looking to see if this is equal or not equal to. Remember, a hole that is too large or too small is going to be a problem. So our test will be a two-tailed test, not equal to 1.84 centimeters. It's also good practice just to state your alpha level or your significance level in your problem so we know exactly what level of significance we're using. Now, in order to test a hypothesis, we have to do two things. We have to create a test statistic based on our data, and we also must have a critical value, or in this case critical values, to compare that test statistic to. Let's start by finding the critical value and discussing how to do that. On page 795 of your textbook, in the very back, you're going to find a t-table to help you find the critical table. It's a value for a one-tailed test. Notice the bold heading at the top. We have a two-tailed test. So in order to be able to use the table to find the critical values, we must divide our alpha level in half. So I'm going to take 0.10 and divide that in half. Alpha over 2, 0.10 over 2, or 0.05. We would like to look and see where this lines up with the degrees of freedom. Recalling that the degrees of freedom is the number of data points minus 1. In this case, we have 12 data points. Minus 1 gives us a degree of freedom of 11. Looking at degrees of freedom of 11 and a 0.05 t significance level, a critical value of 1.796 is read off the table. Let's take a look at what this means. This is a two-tailed test, which means there are actually two critical values, a positive and a negative. The value from the table, 1.796, and the negative equivalent, 1.796. We're going to calculate a test statistic based on our data. If the test statistic, or t-value, is in between these two critical values, we say the data supports HO, or the null hypothesis. If the data is not in between these two critical values, either greater than 1.796 or less than negative 1.796, we say this is in the rejection region. So these two indicate rejection region, or to reject HO. The next thing we're going to do is actually go ahead and calculate a test statistic. right? The t-value from our actual data. Now the t-formula deals with comparing the average. So we take the average from our data, subtract the mean we think is equal to, divide by s, standard deviation, over the square root of n. Now some of these values I'm able to fill in right away. Remember, we think the average is equal to 1.84 centimeters. That is my mu value. I'm also able to fill in there are 12 data points from the given data. However, I do not have the x-bar, the sample average, or the sample standard deviation. So I'm going to use Excel to help me find these. I've entered the data into a column of Excel exactly as it was presented on the problem. I'm going to go to the Formulas tab and insert a function looking for the average first. Once you've found the average value, all you have to do is highlight the data you would like Excel to find the average of. Hit OK, and we have our average value. We'll do something similar to find the standard deviation. I'll insert a function, this time searching for standard deviation. Now, you may notice a couple of different options that come up depending on the version of Excel that you are using. You may see stdev.s or stdevs, right, depending on the version. We do want to find sample standard deviation. I'm going to highlight the 12 data points that are the sample, being careful not to include the average in that value because it's not part of the sample, and I'm finding the standard deviation. These can be used in my formula. I'm going to round each of them to 3 decimal places. So the average from Excel was 1.851. The standard deviation 0.024. I'll then use a normal calculator to calculate the top of the fraction, 1.851 minus 1.84 is 0.011. And on the bottom, I'll take 0.024 and divide by the square root of 12. Lastly, I'll divide the top and the bottom of my fraction to get a t-value of 1.59. Now that I have my test statistic, or t-value, I can compare that to my critical values. If you notice, and I were to graph the test statistic onto my little number line up here, the 1.59 value may fall somewhere about here. Here's my test statistic, or t. This is not in the rejection region. This is in the support the null hypothesis region. So we say the null hypothesis is not rejected. There is not enough evidence at the 10% level of significance to conclude that the mean is any different from 1.84. Recall, we cannot prove that the mean is actually 1.84. We just say there is not enough evidence to reject at this level of significance that the average value is equal to 1.84.